Welcome, everybody. My name is Ricardo Camacho, and thank you for joining us today for this demonstration to see how Parasoft easily integrates C and C++ software testing into your embedded development workflow and help you achieve compliance demands in static analysis, unit testing, structural code coverage, and much, much more. Anyways, now before we get started, let's go through some housekeeping. First, everybody's microphone has been muted. However, if you have questions, please enter them into the question dialog box, and there's also a chat. You can do this at any time. Also, this presentation is being recorded and will be made available within 24 hours. Now, today's demo, our presenter is Miroslav Zielinski, and since we have a lot to show you in a limited amount of time, today's demo is pre-recorded. However, we have a solution architect available, Andre Madan, for Q&A at the end of this presentation, and he will answer all your questions live. Now, next month, we're going to air a brand new exciting demo of C++ test in action. Also, if you would like a personalized demo, let us know by following the link. Okay, we are just about ready to start, but there is one other point to cover. Be aware that when I transition to playing the video, you will initially see a black screen. If you don't see the presentation starting, you may need to refresh your web page. If you have problems, please let us know by way of the chat or question dialog box. And if enough people are experiencing a problem, I will restart the video. Okay, so let's get started.
Welcome. In this short demonstration, I'm going to show you how Parasoft C++ test can help you create high-quality, safe and secure C++ software. Before we dive into the demonstration, let me share some facts about our solution. Parasoft C++ test is a TÜV-certified code testing tool that offers a unique and unified combination of capabilities, which includes static analysis with bug finding, duplicate code detection, code metrics and coding standards compliance, unit testing with a Stubbing framework and the execution on the host and on the target hardware, code coverage with various metrics, and reporting, which simplifies issue remediation and compliance activities. With this combination of testing technologies, Parasoft C++ test is a great product to help you not only with creating high-quality C++ source code, but also to achieve compliance with various industry standards. Standards such as ISO 26262, IEC 61508, or IEC 62304, they recommend or mandate many testing methods and objectives. Satisfying those requirements with disparate code testing tools can be a real nightmare. With C++ tests enforcing MISRA compliance, creating unit tests, measuring code coverage and correlating testing results with requirements becomes much simpler. Not to mention the automated report generation, which reduces tedious paperwork required by the compliance standards. In a nutshell, with C++ test, your compliance journey becomes shorter and less expensive. To take the full advantage of C++ test, it's recommended to deploy it as a part of the CI/CD and at the developer's desktop. Let me walk you through the recommended and typical setups. First, C++ test can be used at the developer's desktop for quick local scans that happen before code commits. Developers run these quick analysis sessions, which help them eliminate the majority of the problems without imposing too much overhead. Once the code is tested locally, it is committed to the repository, which triggers the CI/CD pipeline, where C++ tests perform extensive scans to check if the integrated code satisfies the quality and compliance requirements. If quality or compliance requirements are not met, C++ tests will break the build. Then the CI/CD testing results are delivered back to the developers for remediation through the CI/CD platform's web interface or via Parasoft DTP, our web-based reporting and test data analytics system. DTP brings a huge value to the compliance process. It is TÜV certified and its interactive reporting help in compliance process monitoring. You can also use it for static report generation to support code audits. Now that we have a general understanding or big picture, let's see some of this in action. We will start with the static analysis capabilities of CC++ test. So let me bring our solution. What you can see here is C++ Test Professional. It's available as a plugin to Visual Studio, Eclipse and Eclipse-based embedded IDEs. We also support Visual Studio Code. I have a couple of example projects that I will be using for the demonstration. First, I would like to show you how static analysis helps detect bugs. Let's start analysis using a pre-configured selection of static analysis checkers that perform in-depth data and control flow analysis to detect real runtime problems. Once the analysis finishes, the quality tasks view is loaded with the collection of findings. Let's pick one of the problems. Here we have a violation of the rule avoid division by zero. The violation informs me that I may have a division by zero in my application, and this specific field in my struct is the zero value carrier. As you can see, the finding is presented in the form of the path showing all elements of the violation. When clicking on the path's elements, C++ Test highlights the relevant lines of the source code. The violation takes me through all the steps required to understand the problem. When I click on the first element of the path, C++ Test shows me the code's location where the zero value is assigned to one of the fields in the struct. Here, in the next step, we see it is passed to display personal info function, where, as you can see in the selected line, it is used for the division, which is obviously something we want to avoid. Let's take a look at one more example. Here we have a violation of the rule avoid use before initialization. As you can see, p variable of person pointer type is declared here without initialization. The code below intends to initialize it, but it does so only when fopen call succeeds, which, as we all know, may not always be the case. In such situations, free function is called with an uninitialized pointer, resulting in undefined behavior. Obviously, this is something we don't want to have in our application. In the demonstration so far, we have just seen two examples of interesting static analysis findings, which may be a source of serious runtime problems. C++ Test comes with many more static analysis checkers that can find real bugs in your code. What I'm showing now is the configuration panel that allows enabling and disabling specific static analysis checkers for your code scans. As you can see, the selection of checkers is very rich. We call them static analysis rules. Rules are grouped into rule sets that correspond either to specific aspects of C and C++ programming languages or to industry standards. With this wealth of static analysis checkers, C++ Test is a great tool for coding standards enforcement. It provides the most complete coverage for the popular safety and security coding standards. Here you can see the pre-configured selections of rules for enforcing compliance with standards such as CERT, MISRA, AUTOSAR, and many others. So let's take a quick look and see if our demo project is compliant with MISRA C2012 standard. I'm going to run the analysis now, so let me select the appropriate configuration and wait a second for the results. Clearly, this code was not designed with compliance in mind. We have almost 400 violations. All the findings are reported as violations of MISRA guidelines, so there is no need for additional remapping. Let's pick one of the violations. Here we see the violation of MISRA Directive 4.14, which states that validity of values received from external sources shall be checked. This rule detects cases when unvalidated input, tainted data, is used in an arithmetic operation that can result in numeric overflow or underflow and is later used in dangerous operation. If we need more information, we can quickly see the rule documentation, which provides some additional details and help understand the essence of the problem and strategies to remediate. In our specific case, the first item in the path shows that we are reading some data from the socket. In the next step, this data, without any validation, is used for allocating the memory, which can be potentially harmful to our system. This code obviously violates MISRA Directive 4.14. In the quality task view, we have many more violations, which, if we want to be compliant, we will have to review and fix. Optionally, if we disagree with the tool diagnosis or we have a good reason to deviate from the standard, we can suppress the violation. With Parasoft tool suite, teams have several options for suppressing. Depending on their preferences, violations can be suppressed by adding the source code comment, by adding a suppression record to the plain text file that gets stored with the source code, or by using Parasoft DTP external storage. Here I will suppress the violation by adding the comment to the code. This problem will no longer be reported. Our compliance report will contain information about suppressed violations, but they will be excluded from the findings that need to be fixed. And since we're talking about the coding standards compliance, the very important part of it is compliance reporting. In case of MISRA, for example, the requirements for compliance reporting are very well defined. There is a separate standard called MISRA 2020 Achieving Compliance, which precisely describes the reports that have to be prepared to claim compliance. And here is where Parasoft DTP provides a huge value. It is a TÜV certified reporting and analytics tool which includes a unique compliance reporting for MISRA. The reporting conforms to MISRA 2020 Achieving Compliance standard. With DTP, in addition to the dashboard, which helps me to understand my progress and make a decision about team efforts allocation, I can automatically generate reports that are required to claim MISRA compliance, including Guidelines Enforcement Plan, Guidelines Recategorization Plan, Deviations Report, and finally MISRA Compliance Report. All of them are available with a single click, what eliminates a lot of effort and tedious manual work. In our short demonstration, we have focused on the MISRA compliance, but DTP provides dedicated reporting also for other standards such as CERT or AutoSAR, as well as rich capabilities for unit testing and code coverage. And this concludes the static analysis part of our demonstration. Now we will discuss runtime testing capabilities. Before we dive into the live demonstration part of C++ test unit testing, let me share with you a couple of facts. Our unit testing framework is entirely based on the source code, without any proprietary data formats. It supports C and C++ programming languages. The framework is TÜV certified for ISO 26262, IEC 61508 and IEC 62304, which satisfies tool qualification requirements. For DO178BC, qualification kit is available. C++ test users can create unit tests by typing the code using a graphical editor or automatic generation, which simplifies the process of creating unit test cases. Unit testing is integrated with Stubbing framework, which allows the isolation of any function or method call from the rest of the codebase. Stubs can be configured to perform any action required for the test scenario. Tests can be executed on the host, simulator, and real target hardware, in all cases with code coverage monitoring. C++ tests can also support your integration and system-level testing by measuring the code coverage from those practices. So let's see some of this in action. Let me bring up C++ test. I have a simple example project here that simulates an ECU with a temperature sensor. For my project, I have a complete set of requirements and test specifications defined in my requirements management system. I will start our demonstration by running my system level test and checking the level of code coverage to understand the completeness of my testing. I'm using now a dedicated test configuration that instruments the source code for code coverage metrics, execute instrumented application, and capture its output in the Eclipse console. This is a very simple app. All it does is print some information. My system level test is derived from requirement, and I have it here in my requirements management system. As part of my test, I need to check if the sequence of messages on the console is correct. Such a test would be typically executed in the fully automated mode as a part of CI/CD. Here we have executed it locally. Let's assume that the application output shown in the console satisfies our test requirement, and we want to check the code coverage to see how thorough our testing is. Let me open the code coverage view. Here I can investigate details of collected code coverage. The view is configured now to show line coverage. All other metrics are supported. The summary shows that I have a pretty high level of code coverage from my system tests, but still not 100%. I will be focusing now on using unit tests to ensure that my testing is complete and achieve 100% code coverage. So let me jumpstart my unit testing with the automatic generation of tests. I will use another test configuration to generate an initial set of test cases automatically. C++ test is analyzing the source code now, looking for combinations of function inputs that help achieve deep code penetration. The generated test cases are stored as source code and can be inspected, manually refined, and if suitable, correlated with requirements. Let's take a quick look into tests generated for the handle sensor value function. These automatically generated test cases contain preconditions initialization, where tested function arguments and global variables are initialized, tested function call, and results reporting macros, which can be automatically converted to assertions. Generated test cases are ready for execution. Let's run them and see if our coverage increases. Tests finished. As we see, we were able to improve the penetration of our code. Now we have 95% of the code coverage. The next step with generated test cases is to review them, analyze the results, confront them with requirements, and update assertions to match the low-level requirements for our software unit. And working with requirements is a very important aspect of the unit testing practice in functional safety projects. C++ test supports working with requirements on many levels. The requirements view I've just used when working with automatically generated test cases contains requirements and test specification imported from my requirements management system. With this view, I can analyze requirements and the test specifications and work on my code and tests without switching the context, which improves my productivity. What I just did was enhancing the automatically generated test case to match my requirements test specification. Now I can connect it to the test specification and what follows the requirement. This correlation will be used for generating a traceability report. Let's see another requirement and check if it's correctly implemented. This requirement specifies what should happen in case of sensor failure. On error detection, we are expected to send error message to output, exit the processing loop, report error code, and enter fail-safe mode. It seems that our implementation does what it's supposed to do. However, looking at the code coverage, we clearly see that this error handling branch was never tested. This is because we didn't have sensor failure during our tests, and we do not have any test case associated with this requirements test specification. Missing test case implementation is indicated in my requirements view by this little exclamation mark icon. So what we want to do now is create a test case for main loop function, create a stub for read sensor to simulate the hardware failure, add assertion to make sure that the appropriate error code is returned from the test, and correlate the test case implementation with our requirements test specification. C++ test provides a huge value here. Its stubbing framework can be applied to replace the call to read sensor with an alternative version of the function and simulate the error condition. Let's create a stub for the read sensor. I'm switching now to the stubs view. Here I have my function. As you can see, the original definition is used in my test setup. Now I will create a stub. C++ test automatically generates the stub body. Now with the stub, I'm ready to implement my failure mode test case. In our demonstration, we'll work with the graphical wizard for creating test and stub configuration, but users are free to do it just by typing the code. So I'm going to add a new test case now. We'll name it failure mode test. Here you can see the editor with the table-like representation of the test case. It contains a collection of steps that I can edit. The main loop function does not take any arguments, so we don't need to configure any input values. It uses a global variable messages, but for our failure mode test case, we can ignore it and stay with null initialization. What we want to do, however, is to add a stub configuration to simulate the failure. Let's add the stub configuration for the read sensor. I need to specify the stubbed function name, and here we want to set the return value to status failed, which simulates the hardware failure. And obviously we want to add an assertion that controls if an error exit code is returned, so let me do it here. Alright, and that's it. We're ready to execute this test case. Oh, there is one more thing I need to do. My new unit test was created to validate a specific requirement. So let me annotate this new test case now with the requirement ID. And we are ready for the execution. Our test case has passed. We are happy with the result and we reached 100% of the code coverage. However, our 100% coverage was achieved for the line coverage metric. For safety-oriented projects, we may need other metrics, including MCDC coverage. So let me switch the view for a moment to show us MCDC coverage results. Here we are lucky because the tests that have been prepared give us also 100% of the MCDC coverage. Now we can take a look into DTP and see the traceability report, which documents our testing achievements in the context of requirements. These reports are critical for functional safety standards compliance. Parasoft integrates with the most popular requirements management systems such as JAMA, Polarion or Codebeamer and provides bidirectional traceability between requirements, source code, test results and coverage. DTP can propagate test results to the original system of record, so they can be also visualized in JAMA, Polarion or Codebeamer. Here, as you can see, I have a DTP traceability report. My testing results are presented in the context of requirements. Here I can get the information about the executed test cases, their status, achieved level of code coverage, and also the number of coding standards violations. This is everything that I need to control my compliance process and drive my project to successful certification. And this concludes our demonstration. Thank you for watching.
Well, that was an excellent presentation on C++ test. It really gives a very well-rounded understanding of our solution. Now, if you want to learn more about C++ test or some of our other solutions, you can request a custom in-depth demo. So follow the link or send us an email at info@parasoft.com. Also, as you can see, I've added some QR codes on very informative collateral, including topics and some of our other product solutions. Okay, so I'm now going to pass it over to our solution architect, Andre Madan, for Q&A. Andre?
All right, yeah, Ricardo, can you hear me?
Yes, I can hear you.
All right, perfect. Yeah, it was a pretty cool demo. Let me find some questions. Okay, so the first question that was asked is, can Parasoft collect code? Okay, all right. Can Parasoft collect code coverage from an embedded target when using our own testing framework? Yeah, it's a good question. Many people nowadays for various embedded systems are building their own testing frameworks using Python or using some other open source testing framework. Parasoft can totally support that with our application level coverage. Mirek alluded to that during his demo, but he called it like a system level testing. So the same mechanism that Mirek was outlining for system level testing can be applied to integration level testing or component level testing using your own framework. We would instrument your code outside of the IDE, basically baking our instrumentation in your build process. And then without an IDE, we can just do it and then showing the code coverage once we get the results back. Our runtime library will allow you to collect code coverage not only from not only from systems that support file systems where we can output that easily to a file, but also systems that have serial communication, that have TCP/IP communication. We also have extensibility in our runtime library to add your own communication channel. So, for example, if you're using some interesting mechanism to communicate with a target, which is not, let's say, open or public or proprietary, we can definitely give you source code for the runtime library that can easily be extended to support your communication channel. So, good question, by the way. All right, so the other question, so let me scroll down a little bit. All right, so can developer, okay, that's a good question. So can developers execute static analysis shown on this demo without an IDE? What about unit tests? Okay, so let's just digest that question. I guess in the demo, Mirek was showing a lot of IDE interaction, meaning all of the actions were performed using clicks and drop downs and looking at the IDE. But can those actions also be taken from a command line? Absolutely, yes. We support static analysis running from a command line locally. I know a lot of people are not using IDE today because they're using Vim or VI or Emacs or some remote editors. Some people even use like Visual Studio Code, which, by the way, we support. So yes, all of the actions performed today during the presentation can be done from a command line. As a matter of fact, our testing framework is very command line friendly because it's not GUI driven. So the code for your unit tests is just pure C or C++ code. You can open it up with your own editor and make any modifications just like you do with code. So yeah, so that's that. All right, those were the questions I have in my queue. Ricardo, do you have any other questions in your queue?
No, we don't. Thank you, Andre. That was very helpful. And just to let everybody know, next month we're going to have a brand new exciting demo of C, C++. So please come to our website and register for the event. I thank you very much for attending and look forward to seeing you next month. Thank you, everybody.
Bye. Thank you, everybody.
Bye-bye.